Unit 9 Coordination Compounds. Coordination compounds are the backbone of modern inorganic and bioinorganic chemistry and chemical industry. In the previous unit, we learned that the transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecules by sharing of electrons. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compound is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital components of biological system. Chlorophyll, hemoglobin and vitamin B12 are coordination compounds of magnesium, iron and cobalt respectively. Variety of metallurgical processes, industrial catalysts and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplating, textile dyeing and medicinal chemistry. 9.1 Werners Theory of Coordination Compound. Alfred Werner, 1866 to 1919, a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of a primary valence and a secondary valence for a metal ion. Binary compounds such as CrCl3, CoCl2 or PdCl2 have primary valence of 3, 2 and 2 respectively. In a series of compounds of cobalt third chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate solution in cold, but some remained in solution. 1 mole of CoCl3 into 6NH3, that is yellow in color, gave 3 mole of AgCl. 1 mole of CoCl3 into 5NH3, that is purple in color, gave 2 mole of AgCl. 1 mole of CoCl3 into 4NH3 is green in color, gave 1 mole of AgCl, and again 1 mole of CoCl3 and into 4NH3, that is violet in color, gave 1 mole of AgCl. These observations together with the results of conductivity measurement and solution can be explained if number 1, 6 groups in all, either chloride ions or ammonium molecules, are both remain bonded to the cobalt ion during the reaction, and number 2, the compounds are formulated as shown in table 9.1, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples, the secondary valences are 6. Note that the last two compounds in table 9.1 have identical empirical formula, CoCl3 into 4NH3, but distinct properties. Such compounds are termed as isomers. Werner in 1898 propounded his theory of coordination compounds. The main postulates are number 1, in coordination compounds, metals show two types of linkages, that is valences, primary and secondary. Number 2, the primary valences are normally ionizable and are satisfied by negative ions. Number 3, the secondary valences are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. Number 4, the ions or groups bound by the secondary linkages to the metals have characteristic spatial arrangement corresponding to different coordination numbers. In modern formulations, such spatial arrangements are called coordination polyhedra. The species within the square bracket are coordination entities or complexes, and the ions outside the square bracket are called counter ions. He further postulated that octahedral, tetrahedral and square planar geometrical shapes are more common in coordination compounds of transition metals. The CONH3 whole 6 to the whole 3 positive and COCl NH3 whole 5 to the whole 2 positive and COCl2 NH3 whole 4 to the whole positive are octahedral entities, while NiCO whole 4 and PtCl4 to the whole 2 negative are tetrahedral and square planar respectively. Difference between a double salt and a complex. Both double salts as well as complexes are formed by the combination of two or more stable compounds in a stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, KCl, MgCl2 into 6H2O, Mohr's salt, that is FeSO4, NH4 whole twice, SO4 into 6H2O, potash Lm, Kal, SO4 whole twice into 12H2O, etc. dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN whole 6 to the whole 4 negative of K for FeCN whole 6 do not dissociate into Fe2 positive and Cn negative ions. A small para about Werners. And Werner was born on 12 December 1866 in Mulhouse, a small community in the French province of Alaska. His study of chemistry began in Karlsruhe, Germany and continued in Zurich, Switzerland, where in his doctoral thesis in 1890 he explained the difference in properties of certain nitrogen-containing organic substances on the basis of isomerism. He extended von Hoff's theory of tetrahedral carbon atom and modified it for nitrogen. Werner showed optical and electrical differences between complex compounds based on physical measurements. In fact, Werner was the first to discover optical activity in certain coordination compounds. He, at the age of 29 years, became a full professor at Technische Hochschule in Zurich in 1895. Alfred Werner was a chemist and educationist. His accomplishments include the development of the theory of coordination compounds. This theory, in which Werner proposed revolutionary ideas about how atoms and molecules are linked together, was formulated in a span of only 3 years, from 1890 to 1893. The remainder of his career was spent gathering the experimental support required to validate his new ideas. Werner became the first Swiss chemist to win the Nobel Prize in 1913 for his work on the linkage of atoms and the coordination theory. 9.2 Definition of some important terms pertaining to coordination compounds. A. Coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, COCl3 whole NH3 whole 3 is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Other examples are NiCO whole 4, PtCl2NH3 whole twice, FeCN whole 6 to the whole 4 negative and CONH3 whole 6 to the whole 3 positive. B. Central atom or ion. In a coordination entity, the atom or ion to which a fixed number of ions groups are bound in a definite geometrical arrangement around it is called a central atom or ion. For example, the central atom or ion in the coordination entities, that is NiCl2H2O whole 4, COClNH3 whole 5 to the whole 2 positive and FeCN whole 6 to the whole 3 negative or Ni2 positive, CO3 positive and Fe3 positive respectively. These central atoms or ions are also referred to as Lewis acids. C. Ligands. The ions or molecules bound to the central atom or ion in the coordination entity are called ligands. These may be simple ions such as Cl negative, small molecules such as H2O or NH3, larger molecules such as H2N, CH2, CH2NH2 or N, CH2, CH2NH2 whole thrice or even macromolecules such as proteins. When a ligand is bound to a metal ion through a single donor atom as with chloride ion, H2O or NH3, the ligand is said to be unidentate. When a ligand can bind through 2 donor atoms as in H2N, CH2, CH2NH2, that is ethane 1,2 diamine or C2O4 2 negative oxalate, the ligand is said to be didentate. And when several donor atoms are present in a single ligand as in N, CH2, CH2NH2 whole thrice, the ligand is said to be polydentate. Ethylene diamine tetraacetate ion, that is EDTA 4 negative, is an important hexadentate ligand. It can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. When a di or polydentate ligand uses its 2 or more donor atoms simultaneously to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called the denticity of the ligand. Such complexes called chelate complexes to be more stable than similar complexes containing unidentate ligands. Ligands which has 2 different donor atoms and either of the 2 ligates in the complex is called ambidentate ligand. Examples of such ligands are the NO2 negative and SCN negative ions. NO2 negative ion can coordinate either through nitrogen or through oxygen to a central metal atom or ion. Similarly, SCN negative ion can coordinate through the sulfur or nitrogen atom. D. Coordination number. The coordination number, that is Cn, of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ions PtCl6 to the whole 2 negative and NiNH3 whole 4 to the whole 2 positive, the coordination number of Pt and Ni are 6 and 4 respectively. Similarly, in the complex ion FeC2O4 whole thrice to the whole 3 negative and COEn to the whole 3 to the whole 3 positive, the coordination number of both Fe and cobalt is 6 because C2O4 2 negative and En, that is ethane 1,2 diamine, are didentate ligands. It is important to note here that coordination number of the central atom or ion is determined only by the number of sigma bonds formed by the ligand with the central atom or ion. Pi bonds, if formed between the ligand and the central atom or ion, are not counted for this purpose. E. Coordination is fair. The central atom ion and the ligands attached to it are enclosed in a square bracket and is collectively termed as the coordination is fair. The ionizable groups are written outside the bracket and are called counterions. For example, in the complex K4FeCN whole 6, the coordination is fair is FeCN whole 6 4 negative and the counterion is K positive. F. Coordination polyhedron. The spatial arrangement of the ligand atoms which are directly attached to the central atom or ions defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar and tetrahedral. For example, CONH3 whole 6 3 positive is octahedral, NiCO whole 4 is tetrahedral and PtCl4 whole 2 negative is a square planar. Figure 9.1 shows the shapes of different coordination polyhedra. G. Oxidation number of central atom. The oxidation number of central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parenthesis following the name of the coordination entity. For example, oxidation number of copper in CuCN whole 4 to the whole 3 negative is +1 and it is written as Cu1. H. Homoleptic and heteroleptic complexes. Complexes in which a metal is bound to only one kind of donor groups. Example, CONH3 whole 6 to the whole 3 positive are known as homoleptic. Complexes in which a metal is bound to more than one kind of donor groups. Example, CONH3 whole 4 Cl2 to the whole positive are known as heteroleptic. 9.3 Nomenclature of coordination compounds. Nomenclature is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names. Particularly when dealing with isomers, the formulas and names adopted for coordination entities are based on the recommendations of the International Union of Pure and Applied Chemistry, that is IUPAC. 9.3.1 Formulas of mononuclear coordination entities. The formula of compound is a shorthand tool used to provide basic information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination entities contain a single central metal atom. The following rules are applied while writing the formulas. Number 1. The central atom is listed first. Number 2. The ligands are then listed in alphabetical order. The placement of a ligand in the list does not depend on its charge. Number 3. Polydentate ligands are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. Number 4. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligands are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses. Number 5. There should be no space between the ligands and the metal within a coordination is fair. Number 6. When the formula of a charged coordination entity is to be written without that of the counterion, the charge is indicated outside the square brackets as a right superscript with the number before the sign. For example, COCN whole 6 to the whole 3 negative, CrH2O whole 6 to the whole 3 positive, etc. Number 7. The charge of the cations is balanced by the charge of the anions. 9.3.2 Naming of mononuclear coordination compounds. The names of coordination compounds are derived by following the principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. They are listed as prefixes to the name of the central atom along with any appropriate multipliers. The following rules are used when naming coordination compounds. Number 1. The cation is named first in both positively and negatively charged coordination entities. Number 2. The ligands are named in alphabetical order before the name of the central atom or ion. This procedure is reversed from writing formula. And number 3. Names of the anionic ligands end in O. Those of neutral and cationic ligands are the same except aqua for H2O, amine for NH3, carbonyl for CO, and nitrosyl for NO. While writing the formula of coordination entity, these are enclosed in brackets. Number 4. Prefixes mono, di, tri, etc. are used to indicate the number of the individual ligands in the coordination entity. When the names of the ligands include a numerical prefix, then the term bis, tris, and tetrakis are used, the ligand to which they refer being placed in parentheses. For example, NiCl2 PPH3 whole twice is named as dichlorirobis, that is triphenyl phosphine nickel second. Number 5. Oxidation state of the metal in cation, anion or neutral coordination entity is indicated by Roman numeral in parentheses. Number 6. If the complex ion is a cation, the metal is named same as the element. For example, cobalt in a complex cation is called cobalt and platinum is called platinum. And if the complex ion is an anion, the name of the metal ends with the suffix ate. For example, cobalt in a complex ion, anion, that is cobalt SCN whole 4 to the whole 2 negative is called cobaltate. For some metals, the Latin names are used in the complex anions, example ferrate for Fe. Number 7. The neutral complex molecule is named similar to that of the complex cation. The following examples illustrates the nomenclature for coordination compounds. Number 1. CrNH3 whole thrice, H2O whole thrice to the whole Cl3 is named as triamine triaqua chromium third chloride. Explanation. The complex ion is inside the square bracket, which is a cation. The amine ligands are named before the aqua ligands according to alphabetical order. Since there are 3 chloride ions in the compounds, the charge on the complex ion must be +3 since the compound is electrically neutral. From the charge on the complex ion and the charge on the ligands, we can calculate the oxidation number of the metal. In this example, all the ligands are neutral molecules, therefore the oxidation number of chromium must be the same as the charge of the complex ion +3. Number 2. CO, H2N, CH2, CH2, NH2 whole thrice to the whole twice, SO4 whole thrice is named as tris in bracket ethane 1,2 diamine bracket close cobalt third sulfate. Explanation. The sulfate is the counter anion in this molecule. Since it takes 3 sulfates to bond with 2 complex cations, the charge on each complex cation must be +3. Further, ethane 1,2 diamine is a neutral molecule, so the oxidation number of cobalt in the complex ion must be +3. Remember that you never have to indicate the number of cations and anions in the name of an ionic compound. Number 3. AgNH3 whole twice bracket close AgCN whole twice is named as diamine silver 1 dicyanido argentate 1. 9.4 Isomerism in coordination compound. Isomers are 2 or more compounds that have the same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical or chemical properties. 2 principal types of isomerisms are known among coordination compounds, each of which can be further subdivided. A. Stereoisomerism, that is geometrical isomerism, optical isomerism. B. Structural isomerism, so 4 types are here: linkage isomerism, coordination isomerism, ionization and solvate isomerism. Stereoisomerisms have the same chemical formula and chemical bonds, but they have different spatial arrangement. Structural isomers have different bonds. A detailed account of these isomers are given below. This type of isomerism arises in heteroleptic complexes due to different possible geometric arrangements of the ligands. Important examples of this behavior are found with coordination numbers 4 and 6 in a square planar complex of formula MX2L2, where X and L are unidentate. The 2 ligands X may be arranged adjacent to each other in a cis isomer. or opposite to each other in a trans isomer as depicted in figure 9.2. Other square planar complex of the type MABXL, where ABXL are unidentates, shows 3 isomers, 2 cis and 1 trans. You may attempt to draw these structures. Such isomerism is not possible for a tetrahedral geometry, but similar behavior is possible in octahedral complexes for formula MX2L4, in which the 2 ligands X may be oriented cis or trans to each other. This type of isomerism also arises when didentate ligands, that is LL, example NH2, CH2, CH2, NH2, EN, are present in complexes for formula, that is MX2L, single bond L to the whole twice, figure 9.4. Another type of geometrical isomerism occurs in octahedral coordination entities of the type Ma3B3, like CONH3 whole thrice, NO2 whole thrice. If 3 donor atoms of the same ligands occupy adjacent positions at the corners of an octahedral face, we have the facial isomer. When the positions are around the meridian of the octahedron, we get the meridional isomer. 9.4.2 Optical isomerism. Optical isomers are mirror images that cannot be superimposed on one another. These are called as enantiomers. The molecules or ions that cannot be superimposed are called chiral. The two forms are called dextro D and levo L, depending upon the direction they rotate the plane of polarized light in a polarimeter. D rotates to the right, L rotates to the left. Optical isomerism is common in octahedral complexes involving didentate ligands. In a coordination entity of the type PTCl2 En whole twice to the whole 2 positive, only the cis isomer shows optical activity. 9.4.3 Linkage isomerism. Linkage isomerism arises in a coordination compound containing ambidentate ligand. A simple example is provided by complexes containing the thiocyanate ligand NCS negative, which may bind through the nitrogen to give MNCS or through sulfur to give MSCN. That is, Jorgensen discovered such behavior in the complex CONH3 whole 5 NO2 to the whole Cl2, which is obtained as the red form, in which the nitrite ligand is bound through oxygen, that is ONO, and as the yellow form, in which the nitrite ligand is bound through nitrogen, that is NO2. 9.4.4 Coordination isomerism. This type of isomerism arises from the interchange of ligands between the cationic and anionic entities of different metal ions present in a complex. An example is provided by CONH3 whole 6 CrCN6, in which the NH3 ligands are bound in cobalt 3 positive and the Cn negative ligands to Cr3 positive. In its coordination isomer CrNH3 whole 6 and CN whole 6, the NH3 ligands are bound to Cr3 positive and the Cn negative ligands to CO3 positive. 9.4.5 Ionization isomerism. This form of isomerism arises when the counter ion in a complex salt is itself a potential ligand and can be displaced a ligand which can then become the counter ion. An example is provided by the ionization isomers, that is CONH3 whole 5 SO4 bromine and CONH3 whole 5 bromine to the whole SO4. 9.4.6 Solvate isomerism. This form of isomerism is known as hydrate isomerism in case where water is involved as a solvent. This is similar to ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. An example is provided by the aqua complex CrH2O whole 6 Cl3, that is violet, and its solvate isomer CrH2O whole 5 Cl into Cl2 into H2O, that is grey-green. 9.5 Bonding in coordination compounds. Werner was the first to describe the bonding features in coordination compounds, but this theory could not answer basic questions like number 1, why only certain elements possesses the remarkable property of forming coordination compounds. Number 2, why the bonds in coordination compounds have directional properties. Number 3, why coordination compounds have characteristic magnetic and optical properties. Many approaches have been put forth to explain the nature of bonding in coordination compounds via valence bond theory (VBT), crystal field theory (CFT), ligand field theory (LFT), and molecular orbital theory (MOT). We shall focus our attention on elementary treatment of the application of VBT and CFT to coordination compounds. 9.5.1 Valence bond theory. According to this theory, the metal atom or ion under the influence of ligands can use it N-1d, Ns, Np or Ns, Np, Nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar and so on. Table 9.2. These hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bonding. This is illustrated by the following examples. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of the valence bond theory. In the diamagnetic octahedral complex, the cobalt ion is in +3 oxidation state and has the electronic configuration 3d6. The hybridization scheme is as shown in diagram. 6 pairs of electrons, one from each NH3 molecule, occupy the 6 hybrid orbitals. Thus, the complex has octahedral geometry and is diamagnetic because of the absence of an unpaired electron. In the formation of this complex, since the inner d orbital, that is 3d, is used in hybridization, the complex CONH3 whole 6 to the whole 3 positive is called an inner orbital or low spin or spin paired complex. The paramagnetic octahedral complex COF6 to the whole 3 negative uses outer orbital 4d in hybridization sp3d2. It is thus called outer orbital or high spin or spin free complex. Thus, in tetrahedral complexes, on 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. This is illustrated below for NiCl4 to the whole 2 negative. Here nickel is in +2 oxidation state and the ion has the electronic configuration 3d8. The hybridization scheme is as shown in diagram. Each chlorine ion donates a pair of electrons. The compound is paramagnetic since it contains 2 unpaired electrons. Similarly, NiCO whole 4 has tetrahedral geometry but is diamagnetic since nickel is in 0 oxidation state and contains no unpaired electron. In the square planar complexes, the hybridization involved is dsp2. An example is NiCN whole 4 to the whole 2 negative. Here nickel is in +2 oxidation state and has the electronic configuration 3d8. The hybridization scheme as shown in diagram. Each of the hybridized orbitals receives a pair of electrons from a cyanide ion. The compound is diamagnetic as evident from the absence of unpaired electron. It is important to note that hybrid orbitals do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. 9.5.2 Magnetic properties of coordination compounds. The magnetic moment of coordination compounds can be measured by the magnetic susceptibility experiments. The results can be used to obtain information about the number of unpaired electrons and hence structures adopted by metal complexes. A critical study of the magnetic data of coordination compounds of metals of the first transition series reveals some complications. For metal ions with up to 3 electrons in the d orbitals like Ti3 positive, D1, V3 positive, D2, Cr3 positive, D3, 2 vacant d orbitals are available for octahedral hybridization with 4s and 4p orbitals. The magnetic behavior of these free ions and their coordination entities is similar. When more than 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available as a consequence of Hund's rule. Thus, for D4, chromium 2 positive and chromium 2 positive and Mn3 positive, D5, Mn2 positive and Fe3 positive. In D6, it is Fe2 positive and CO3 positive cases. A vacant pair of d orbitals results only by pairing of 3d electrons, which leaves 2, 1 and 0 unpaired electrons respectively. The magnetic data agree with maximum spin pairing in many cases, especially with coordination compounds containing d6 ions. However, with the species containing d4 and d5 ions, these are complications. MnCN whole 6 to the 3 negative has magnetic moment of 2 unpaired electrons, while MnCl6 to the whole 3 negative has a paramagnetic moment of 4 unpaired electrons. FeCN whole 6 to the whole 3 negative has magnetic moment of single unpaired electron, while FeF6 to the whole 3 negative has a paramagnetic moment of 5 unpaired electrons. COF6 to the whole 3 negative is paramagnetic with 4 unpaired electrons, while COC2O4 to the whole thrice to the whole 3 negative is diamagnetic. The apparent anomaly is explained by valence bond theory in terms of formation of inner orbital and outer orbital coordination entities. MnCN whole 6 to the whole 3 negative, FeCN whole 6 to the whole 3 negative, and COC2O4 to the whole thrice to the whole 3 negative are inner orbital complexes involving D2sp3 hybridization. The former two complexes are paramagnetic and the later diamagnetic. On the other hand, MnCl6 to the whole 3 negative, FeF6 to the whole 3 negative, and COF6 to the whole 3 negative are outer orbital complexes involving sp3d2 hybridization and are paramagnetic, corresponding to 4, 5 and 4 unpaired electrons. 9.5.3 Limitations of valence bond theory. While the VB theory to a larger extent explains the formation, structures and magnetic behavior of coordination compounds, it suffers from the following shortcomings. Number 1, it involves a number of assumptions. Number 2, it does not give quantitative interpretation of magnetic data. Number 3, it does not explain the color exhibited by the coordination compounds. Number 4, it does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. Number 5, it does not make exact predictions regarding the tetrahedral and square planar structures of 4 coordinate complexes. Number 6, it does not distinguish between weak and strong ligands. 9.5.4 Crystal field theory. The crystal field theory CFT is an electrostatic model which considers the metal-ligand bond to be ionic, arising purely from electrostatic interactions between the metal ion and the ligand. Ligands are treated as point charges in case of anions or point dipoles in case of neutral molecules. The 5 d orbitals is an isolated gaseous metal atom or ion have same energy, that is, they are degenerate. This degeneracy is maintained if a spherically symmetrical field of negative charges surrounds the metal atom or ion. However, when the negative field is due to ligands, either anions or the negative ends of the dipolar molecules like NH3 and H2O in a complex, it becomes asymmetrical and the degeneracy of the d orbitals is lifted. It results in splitting of the d orbitals. The pattern of splitting depends upon the nature of the crystal field. Let us explain this splitting in different crystal fields. A. Crystal field splitting in octahedral coordination entities. In an octahedral coordination entity with 6 ligands surrounding the metal atom or ion, there will be repulsion between the electrons in metal d orbitals and the electrons or negative charges of the ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand than when it is away from the ligand. Thus, the dx2 and y2 and dz2 orbitals which point towards the axis along the direction of the ligand will experience more repulsion and will be raised in energy. And the dxy, dyz and dxz orbitals which are directed between the axes will be lowered in energy relative to the average energy in the spherical crystal field. Thus, the degeneracy of the d orbital has been removed due to the ligand electron-metal electron repulsions in the octahedral complexes to yield 3 orbitals of lower energy, T2G set, and 2 orbitals of high energy, EG set. This splitting of the degenerate levels due to the presence of ligands in a definite geometry is termed as crystal field splitting, and the energy separation is denoted by delta naught. The subscript 0 is for octahedral. Thus, the energy of the 2 EG orbitals will increase by 3 by 5 delta naught, and that of the 3 T2G will decreases by 2 by 5 delta naught. The crystal field splitting delta naught depends upon the field produced by the ligand and charge on the metal ion. Some ligands are able to produce strong fields, in which case the splitting will be large, whereas others produce weak fields and consequently result in a small splitting of d orbitals. In general, ligands can be arranged in a series in the order of increasing field strength as given below. Iodine negative is less than, bromine negative is less than, SCN negative is less than, chloride negative is less than, S2 negative is less than, F negative is less than, OH negative is less than, C2O4 2 negative is less than, H2O is less than, NCS negative is less than, EDTA4 negative is less than, NH3 is less than, EN is less than, CN negative is less than, CO. Such a series is termed as a spectrochemical series, and it is an experimentally determined series based on the absorption of light by complexes with different ligands. Let us assign electrons in the d orbitals of metal ion in octahedral coordination entities. Obviously, the single d electron occupies one of the lower energy T2G orbitals in D2 and D3 coordination entities. The d electrons occupy the T2G orbital singly in accordance with the Hund's rule. For D4 ions, two possible patterns of electron distribution arise. Number 1, the fourth electron could either enter the T2G level and pair with an existing electron, or number 2, it could avoid paying the price of the pairing energy by occupying the EG level. Which of these possibilities occurs depends on the relative magnitude of the crystal field splitting. Delta naught and the pairing energy. P represents the energy required for electron pairing in a single orbital. The two options are: number 1, if delta naught is less than P, the fourth electron enters one of the EG orbitals, giving the configuration T2G E1G. Ligands for which delta naught is less than P are known as weak field ligands and form high spin complexes. Number 2, if delta naught is greater than P, it becomes more energetically favorable for the fourth electron to occupy a T2G orbital with configuration T2G for EG0. Ligands which produce this effect are known as strong field ligands and from low spin complexes. Calculations shows that D4 and D7 to D7 coordination entities are more stable for a strong field as compared to weak field cases. B. Crystal field splitting in tetrahedral coordination entities. In tetrahedral coordination entity formation, the d orbital splitting is inverted and is similar as compared to the octahedral field splitting. For the same metal, the same ligands and metal ligand distances, it can be shown that delta T is equals to 4 by 9 delta naught. Consequently, the orbital splitting energies are not sufficiently large for forcing pairing, and therefore low spin configurations are rarely observed. The G subscript is used for the octahedral and square planar complexes which have a center of symmetry. Since tetrahedral complexes lack symmetry, G subscript is not used with energy levels. 9.5.5 Color in coordination compounds. In the previous unit, we learned that one of the most distinctive properties of transition metal complexes is their wide range of colors. This means that some of the visible spectrum is being removed from white light as it passes through the sample. So the light that emerges is no longer white. The color of the complex is complementary to that which is absorbed. The complementary color is the color generated from the wavelength left over. If green light is absorbed by the complex, it appears red. Table 9.3 gives the relationship of the different wavelength absorbed and the color observed. Table 9.3 relationship between the wavelength of the light absorbed and the color observed in some coordination entities. The color in the coordination compounds can be readily explained in the terms of crystal field theory. Consider, for example, the complex TiH2O6 to the whole 3 positive, which is violet in color. This is an octahedral complex where the single electron Ti3 positive is a 3D1 system. In the metal d orbital is in the T2G level in the ground state of the complex. The next higher state available for the electron is the empty EG level. If light corresponding to the energy of blue-green region is absorbed by the complex, it would excite the electron from T2G level to the EG level. Consequently, the complex appears violet in color. The crystal field theory attributes the color of the coordination compounds to DD transition of the electron. It is important to note that in the absence of ligand, crystal field splitting does not occur and hence the substance is colorless. For example, removal of water from TiH2O6 to the whole Cl3 on heating renders it colorless. Similarly, anhydrous CuSO4 is white but CuSO4 into 5H2O is blue in color. The influence of the ligand on the color of a complex may be illustrated by considering the NiH2O6 to the whole 2 positive complex, which forms when nickel chloride is dissolved in water. If the didentate ligand ethane 1,2 diamine is progressively added in the molar ratios, that is En into Ni, that is 1:1, 2:1 and 3:1, the following series of reactions and their associated color changes occur. 9.5.6 Limitations of crystal field theory. The crystal field model is successful in explaining the formation structures, color and magnetic properties of coordination compounds to a large extent. However, from the assumptions that the ligands are point charges, it followed the anionic ligand should exert the greatest grating effect. The anionic ligands actually are found at the low end of the spectrochemical series. Further, it does not take into account the covalent character of bonding between the ligand and the central atom. These are some of the weaknesses of CFT which are explained by ligand field theory and molecular orbital theory which are beyond the scope of the present study. 9.6 Bonding in carbonyls. The hemolytic carbonyls are formed by most of the transition metals. These carbonyls have simple, well-defined structures. Tetracarbonyl nickel is tetrahedral, pentacarbonyl iron is trigonal, bipyramidal, while hexacarbonyl chromium is octahedral. Decacarbonyl D-manganese is made up of two square pyramidal MnCO5 units joined by a Mn-Mn bond. Octacarbonyl dicobalt has a cobalt-cobalt bond bridged by two CO groups. The metal-carbon bond in metal carbonyls possesses both sigma and pi character. The MC sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into a vacant orbital of the metal. The MC pi bond is formed by the donation of a pair of electrons from a filled d orbital of metal into the vacant antibonding, that is pi star orbital of the carbon monoxide. The metal to ligand bonding creates a synergic effect which strengthens the bond between CO and the metal. 9.7 Importance and applications of coordination compound. The coordination compounds are of great importance. These compounds are widely present in the mineral, plant and animal worlds and are known to play many important functions in the area of analytical chemistry, metallurgy, biological systems, industry and medicines. These are described below. Coordination compounds find use in many quantitative and qualitative chemical analysis. The familiar color reactions given by metal ions with a number of ligands, especially chelating ligands, as a result of formation of coordination entities, form the basis for their detection and estimation by classical and instrumental methods of analysis. Examples of such reagents includes EDTA, DMG, that is dimethylglyoxime, and alpha-nitroso, beta-naphthol, cupron, etc. Hardness of water is estimated by simple titration with Na2-EDTA. The calcium 2 positive and magnesium 2 positive ions form stable complexes with EDTA. The selective estimation of these ions can be done due to difference in the stability constants of calcium and magnesium complexes. Some important extraction processes of metals like those of silver and gold make use of complex formation. Gold, for example, combines with cyanide in the presence of oxygen and water to form the coordination entity AuCN whole twice to the whole negative in aqueous solution. Gold can be separated in metallic form from this solution by the addition of zinc. Similarly, purification of metals can be achieved through formation and subsequent decomposition of their coordination compounds. For example, impure nickel is converted to NiCO4 which is decomposed to yield pure nickel. Coordination compounds are the great importance in biological systems. The pigment responsible for photosynthesis, chlorophyll, is a coordination compound of magnesium. Hemoglobin, the red pigment of blood which acts as oxygen carrier, is a coordination compound of iron. Vitamin B12, cyanocobalamin, the anti-pernicious anemia factor, is a coordination compound of cobalt. Among the other compounds of biological importance with the coordinated metal ions are the enzymes like carboxypeptidase and carbonic anhydrase, catalyst of biological systems. Coordination compounds are used as catalyst for many industrial processes. Examples include rhodium complex, that is PH3P whole thrice RHCl. A Wilkinson catalyst is used for the dehydrogenation of alkenes. Articles can be electroplated with silver and gold much more smoothly and evenly form solutions of the complexes, that is AgCN whole twice to the whole negative and AuCN whole twice to the whole negative, than from a solution of simple metal ions. In black and white photography, the developed film is fixed by washing with hypo solution which dissolves the undecomposed AgBr to form a complex ion AgS2O3 whole twice to the whole 3 negative. There is growing interest in the use of chelate therapy in medicinal chemistry. An example is the treatment of problems caused by the presence of metals in toxic proportion in plant-animal systems. Thus, excess of copper and iron are removed by the chelating ligands D-penicillamine and dysferroxim B via the formation of coordination compounds. EDTA is used in the treatment of lead poisoning. Some coordination compounds of platinum effectively inhibit the growth of tumors. Examples are cisplatin and related compounds. Summary: the chemistry of coordination compound is an important and challenging area of modern inorganic chemistry. During the last 50 years, advances in this area have provided development of new concepts and models of bonding and molecular structure, novel breakthroughs in the chemical industry, and vital insights into the functioning of critical components of biological systems. The first systematic attempt at explaining the formation, reactions, structures, and bonding of coordination compound was made by A. Werner. His theory postulated the use of two types of linkages, primary and secondary, by a metal atom or ion in a coordination compound. In the modern language of chemistry, these linkages are recognized as the ionizable and non-ionizable, that is covalent bonds respectively. Using the property of isomerism, Werner predicted the geometrical shapes of a large number of coordination entities. The valence bond theory VBT explains with reasonable success the formation, magnetic behavior, and geometrical shapes of coordination compounds. It, however, fails to provide a quantitative interpretation of magnetic behavior and has nothing to say about the optical properties of these compounds. The crystal field theory CFT to coordination compound is based on the effect of different crystal fields provided by the ligands taken as point charges on the degeneracy of d orbital energies of the central metal atom or ion. The splitting of d orbital provides different electronic arrangements in strong and weak crystal fields. The treatment provides for quantitative estimations of orbital separation energies, magnetic moments, and spectral and stability parameters. However, the assumptions that ligands constitute point charges creates many theoretical difficulties. The metal-carbon bond in metal carbonyls possesses both sigma and pi character. The ligand to metal is sigma bond and metal to ligand is pi bond. This unique synergic bonding provides stability to metal carbonyls. Coordination compounds are of great importance. These compounds provide critical insights into the functioning and structure of vital components of biological systems. Coordination compounds also find extensive applications in metallurgical processes, analytical and medicinal chemistry. Chapter completed. Thank you so much. Students, please share this video as much as possible ताकि हर बच्चे को इसकी help मिल सके. Thank you.